A modern rail line carries a quarter-mile-long steel ribbon welded into a single piece, locked under enough compressive stress on a hot day to snap a concrete pillar. And underneath it, loose rocks. No glue, no bolts, no foundation. Just a pile of sharp stones poured into place by the truckload. Why does the most precise piece of infrastructure on land sit on something a kid could kick apart? Why rocks? Why those rocks? Ask anyone what the stones are for and you'll get a reasonable answer. They hold the track down. They let water drain through. They stop weeds from growing into the rail bed. All of that is true. The stones have a name. Track ballast. They sit underneath and around the wooden or concrete crossbeams that the rails are clipped to, called sleepers or ties. A typical stretch of mainline track has around 2,000 ties per kilometer, each one resting on a bed of crushed stone roughly a foot deep, sometimes deeper. The ballast extends out past the rails on both sides, forming sloped shoulders that shed rainwater. Standard slope ratios run from 1.5 to 1 up to 3 to 1, horizontal to vertical, depending on the line. This is the version you find in textbooks. The ballast distributes the weight of the train, drains water, and controls vegetation. Tidy. Sensible. The kind of explanation that makes you nod and move on. The problem is that none of it explains the specifics. It doesn't explain why the stones have sharp edges instead of smooth ones. It doesn't explain why they're a particular size, between 25 and 60 millimeters. It doesn't explain why railway engineers spend serious money quarrying granite and basalt from specific sources when they're perfectly good river stones lying around for free. And it doesn't explain the strangest thing of all, which is that the rail itself is fighting to escape from those stones every single day. Run your hand through a bucket of beach pebbles. They slide over each other. Pour them into a pile, and that pile flattens out, because every stone is trying to roll away from every other stone. Rounded shapes don't grip. They just don't. Crushed ballast is the opposite. The stones are angular, jagged, and broken at random angles by a rock crusher. When you pour them into place and pack them down, the sharp corners wedge into each other. Every stone is pinned by 3 or 4 neighbors. Push on one and the whole mass resists, because moving one stone means lifting or shoving every stone that's keyed into it. This is called particle interlock, and it's the entire reason crushed stone works as a foundation while gravel doesn't. The rocks themselves are chosen carefully. Granite, basalt, quartzite, hard limestone. Compressive strengths in the range of 100 to 300 megapascals. They're tested with something called the Los Angeles abrasion test, which tumbles a sample of stones in a steel drum with steel balls and measures how much of the rock breaks down into dust. Soft stone fails this test. Soft stone becomes mud. Size matters too. Too small and the stones pack tight, blocking drainage and trapping water. Too large and there aren't enough contact points to spread the load. The sweet spot, somewhere around the size of a chicken egg, gives you enough voids for water to pour through while keeping enough contact between particles to lock the whole layer together. So now the picture sharpens. The ballast isn't just a pile of rocks. It's a deliberately engineered aggregate, sized and shaped to behave almost like a single elastic mat. But there's still a question hanging in the air. What is the ballast actually holding back? The weight of a train is heavy, but the ground underneath can take that. The real reason the stones are there has almost nothing to do with the weight pressing down. It has to do with a force trying to push the track sideways. For most of railway history, tracks came in short segments bolted together with small gaps between them. Those gaps were the reason for the classic clickety-clack of an old train. The gaps existed because steel expands when it gets hot and contracts when it cools, and short rails with gaps between them could grow and shrink freely without doing any damage. Modern rail doesn't work that way. Most mainline track today is continuous welded rail, where individual lengths of steel are welded into segments a quarter of a mile long or more. No gaps, no clickety-clack. A smoother, quieter ride, and far less wear on the wheels. But that steel still wants to expand and contract. And if the rail can't grow, the heat has to go somewhere. It turns into stress, locked-in stress. The numbers are not gentle. A temperature swing of 40 degrees Celsius produces a compressive stress in the rail of around 96 megapascals. That's the equivalent of nearly 14,000 pounds of force per square inch of steel cross-section, pushing outward all day, every hot afternoon. The rail isn't being lazy. It's straining against its own clamps with the force of a hydraulic press, and it has nowhere to go. So it finds a way to go sideways. On a hot enough day, with weak enough lateral resistance, the rail will snake outward in a tight S-curve. Railway people call this a sun kink. Trains derail in sun kinks. People die in sun kinks. The only thing standing between locked-in thermal stress and a derailed train is the lateral resistance of the ballast, the friction of the sleepers sitting on the stone, the wedging force of every angular rock pressed against the side of every concrete tie. Multiply that across 2,000 ties per kilometer, and you get a mass of interlocked stone heavy enough and grippy enough to hold a steel rail in place while it tries to tear itself apart in the heat. That's what the rocks are really for, not to support weight, to resist motion. The thing about a system held together by friction and interlock is that it doesn't stay perfect. Every train that rolls over the track pushes the ballast around a little. The stones grind against each other. Sharp corners get rounded off. Particles crack. Dust builds up. Mud works its way in from below or from above. The industry has a word for this: fouling. Fouled ballast loses its drainage. It loses its interlock. The track starts to settle unevenly, and the smooth geometry that lets a train run at speed begins to warp. The fix is a piece of equipment called a tamper, a long machine that crawls along the track, lifting the sleepers, vibrating new ballast into the gaps underneath, and packing the whole mess back down. Major rail networks tap their busiest lines every couple of years. Eventually, even tamping isn't enough, and the entire ballast layer has to be excavated and replaced. A ballasted track on a heavy-use line might need full ballast renewal every 15 to 20 years. This is expensive. It also requires shutting the line down, which is its own kind of expensive. On a freight corridor running thousands of tons of coal or grain a day, every hour the track is closed is money on the floor. On a passenger line, it means buses replacing trains and angry commuters. And there's the dust. Ballast grinds itself into a fine mineral powder under load, which is one reason train stations near older ballasted track have the familiar gritty smell. There's the noise. Stones don't absorb sound the way concrete does, and a train on ballast rumbles louder than a train on slab. For most of the world's rail network, all of that is still worth it. The materials are cheap. The skills to maintain it are everywhere. A ballasted track can be repaired by a crew of workers with hand tools if it has to be. But at the high end of the railway world, where speeds climb past 250 kilometers per hour, and the geometry has to stay perfect to the millimeter, the stones are starting to lose their job. Walk along a stretch of Japan's Shinkansen line or Germany's high-speed corridor, and in many places you won't see ballast at all. The rails sit on concrete, a continuous slab poured in place with the sleepers cast directly into it. No stones, no tamping, no fouling. The geometry stays where the engineers put it, year after year. This is called slab track, or ballastless track, and on a high-speed line, the math eventually favors it. The construction cost is much higher, sometimes more than double per kilometer, but the maintenance cost is a fraction. Service life climbs from 15 to 20 years, up to 50 or 60. Trains can run faster, smoother, and quieter. Japan has been building it on new lines for over 5 decades, partly because so much of the country's high-speed rail runs on viaducts and through tunnels, where slab track is actually cheaper than ballast, once you account for the structural weight savings. So why is most of the world still on rocks? Cost, mainly. The first 5 years of any new line is dominated by construction spending, and ballasted track wins that comparison by a wide margin. On lower speed routes, on freight lines, anywhere the maintenance pain isn't crushing, the stones keep doing their job. A piece of granite quarried 150 years ago is still working underneath a track somewhere, holding a piece of welded steel in place while it pushes back against the heat. The next time you stand near a rail line, look down. Those rocks aren't decoration. They aren't leftover construction debris. They're a load-bearing foundation, a thermal anchor, a drainage system, and a vibration damper all at once, built out of the cheapest material on Earth. A pile of broken stone, doing the work of a structural engineer who never has to show up. That's the part nobody tells you. The most reliable component of the railway, the one that's been doing the same job since the 1830s, without any real change in design, isn't the locomotive or the rail or the signal system, it's the rocks.